Swayam Prabha. Digital India. Educated India.
Today, let's talk about the thermal stress analysis. So this we are referring to a solid which is heated by a certain degree of temperature, and then this heating of the body will cause the dimensional change in the size of the body. So this obviously will cause equivalent to thermal strains, and this together with the strain caused by the mechanical loads will cause the overall stresses and strains in the body. We also know that these thermal strains can be quite large sometimes and as comparable to the mechanical loads itself. So they may cause huge amount of stresses sometimes. If a body is confined in a space and if it is caused by certain heat, then that temperature change will cause a lot of stresses in the body. So we know it's a very, very important aspect of stress analysis. So in this case, let's just look at this one, say a one-dimensional rod here, for example. If it is subjected to so this is subjected to temperature, this is original, let us say, and this is subjected to heat, maybe steady state, and the temperature raise will be delta T. So what we are saying is that this is a temperature T naught and this is a temperature T, and this will cause a certain change in the thing. So we know that it is equal to this. So this change is alpha times delta T times L naught. If this is L naught, right, where alpha is the thermal expansion coefficient, okay, so that is, and delta T is the change and L naught is the one. So thermal expansion coefficient is change in length divided by original length, and that's per degree temperature. So this is actually alpha is kind of strain equivalent, okay, thermal strain equivalent, and that multiplied by alpha naught will cause the change, and then delta T is the change in temperature. So this is what it is, and together with this one, now so if you subject it to some kind of this, you understand, so load here, and then this is further change in the length, and this is due to change due to Okay, so this is so now the total change here is from L0 to this one, and you can call it in terms of strains. So the total strain epsilon is equal to this is due to this and thermal mechanical. So we can see that the thermal strain and the mechanical strain. Thermal strain, as you can see, though I wrote it in the full change, is nothing but alpha times delta T, right? So this is the thermal strain, and mechanical strain, as we understand, it's given by the stress divided by the Young's modulus, okay? Or we can even say that mechanical strain is total. So why we want to do this one is that this actually the thermal strain is not necessarily due to the thermal effect. It might even be due to many other effects. It can even be due to the hygroscopic effect, okay? Or it can even be just some initial strain as well. So sometimes it is just called initial strain, and on top of it there is a mechanical strain. So this is the mechanical strain component. So this can be, this is, I wrote it in 1D, but this can also be written in 2D. In 2D, the thermal strain is as, let me just see. So the strains, of course, obviously you know that in 2D you have strain, 3 strain components. So the thermal strain part will be alpha delta T, alpha delta T. This is assuming that the material is isotropic. Otherwise, if material is anisotropic, it can even be alpha X, alpha Y, and delta T is the temperature change. So this is the thermal strain, okay? And of course, mechanical strain we know. And so now, if you want to apply without thinking that it is thermal or anything like that, so the total change is here from here. This is the total change, okay? This is the thermal, and this is the mechanical. Okay, so now what we, going by our variation, if you go by the variational approach, here is the energy, internal energy means that elastic energy is due to the mechanical load or mechanical strain. So you can say that this is equal to, so this of course we'll put a half here, and then this is the mechanical, and okay, so this is, and then this is the Q2 integrated over volume. So this we are used to this one. In fact, this, in fact, you can write it as epsilon x So this is how we can right? And then we also know that this is the internal energy. Obviously, we also have to take into account the work of external forces. So here, so the stress here is due to the mechanical component. So this is nothing but your D multiplied by what? The mechanical component here. Okay, so this is the stress in the body. So that's what goes here. Okay, and so I just wrote it as two components, but actually these are the three components in 2D. Like this one, we have to write it as a product. All right. So now, okay, all right, we'll put it here. So here we'll write it as epsilon transpose and d epsilon. So this is all mechanical thing, and then so these mechanical things I'll write it as okay, the mechanical thing. So we will write it as epsilon minus epsilon transpose. I'll just write M here. Please, now these are all components, three components. So just for the sake of conciseness, I'm not writing it all the components here. Otherwise, you understand it. All right. So if you look at this one, so there are two terms here and two terms here with a D there. We can expand it. There are epsilon mechanical transpose here minus epsilon I'm sorry, this is not mechanical, this is thermal, right? I'm sorry. This is thermal, not mechanical. Okay, so this is expanded all the four terms. In fact, there is one thing that you can see here is that epsilon thermal, okay, and times dE epsilon. This is epsilon transpose d epsilon thermal. So these two are scalars, of course, will be equal to each other because here D is a symmetric matrix. So even if you interchange these two, then if you take the product of the three, then the value will be same. So like this. So what we have here, we can, so these two will be the same. So we can combine them. And here, if you do that, do here, . Okay, so now we can convert these things into the displacements. One is that this epsilon here, which consists of three terms. Is nothing but, what is that? In the our terminology of, say, a three-noded triangle, or even for that matter, any element. So this can be written as our B matrix times is UIVI. Just for the sake of convenience, I'm writing it for three-noded triangle. So these are nothing but the nodal displacement. So B times this. So we can even write this as so this is the all the nodal displacements of the element. So you simply write it as UE. And so similarly, epsilon thermal here, just to recall, this is nothing but this is constant. Given the temperature, we can find out. So what is the thermal strain? Okay. So let's simplify this, and then if you do that, so this is nothing but you must be able to recognize what is this. This is the first term. Okay, so this is this term here. And then the second one, we can cancel the half there. And we will write this one, UE transpose B D times epsilon thermal, which is given here. Okay. And what about this one? The last term here, I say we can neglect it. For what reason? So given a problem, given the temperature for us, so this epsilon thermal times T times epsilon thermal is a constant value. So while here, this is going as a part of energy, as a part of potential energy, which we need to differentiate, okay? Which we are going to differentiate dou pi by dou u1, dou pi by dou u2, and so on. So while if you differentiate this one, so since this being a constant, so this will not have any derivative value. So this being constant, so epsilon thermal is dropped here. Okay, this is the internal energy, and apart from this one, we also have other components like the body forces and so on. If you want, we can also include that. So this is the total strain energy. If you want, we can also do that. What is that? So here, these are, now we just for the sake of completeness, we are adding the body forces. Okay, these are the body forces. So this was the strain energy. Now if you write it for the potential energy, we also have to include the work of external forces. And here I write that epsilon thermal times epsilon thermal is constant and will not have any derivatives. And its derivatives with displacements with UE is 0. Right? So this is what I said. So since this being a constant and can be neglected for further analysis. So for the further analysis, so we are going to neglect this term. All right, so now what we have here is that the potential pi here, this is for one element. Okay, you see that this is for one element, and pi, so where pi, we can write this one. So what is this one? So it is, so you can recognize that is nothing but that's F thermal, and apart from that we also have okay. So let me explain these things. So this is concise form. What is that K means? K you can recognize to be the usual stiffness matrix of the element. So here K is the stiffness. Here K of the element is nothing but your integral of P transpose okay. This is nothing but that it, and now apart from that there is something known as here F thermal. F thermal is nothing but V transpose D epsilon. Okay, so this is the vector, the load vector or the force vector that takes into account the thermal expansion. So the thermal expansion now is converted, okay, into an equivalent load. So something like here. So here you have a thermal expansion. You can also say that, okay, you can even convert that by a load. Here, what should be the load that need to be applied to get that kind of epsilon thermal? So that's what we are doing here. And so this is a very simple expression. We can simplify it just now. But okay, let me, this of course you know that this stiffness matrix okay. So we'll explain. So finally what we have here, I'll explain this one, simplify it for three-noded triangle. So what we have here is thermal, So I'm just, for the moment, I'm dropping this usual contribution here by the usual loads, but this is just now the thermal component. And so this is summation over all the elements. So we can say that this is the assembly global so these are all global things where UG is the global and K is of course assembled matrix of, I'm sorry, this is not D, K of the element, and K of the element is assembled into the global matrix, and so this is the global equation. So we know that here that minimizing P pi with respect to E here, we get the usual equation, except that we get a thermal component here, right? Okay, so that's dou pi by dou U global equal to 0. Then this leads to okay, so this is the final equation. So this is as you see it carefully. So this is nothing but our usual difference multiplied by the global displacement vector, and then this is the mechanical load which are applied, and then together with this one to take care of the thermal effect, so we have a thermal force vector here. So that's F thermal. That is the new term which has come. So you add it into this one, and then solve it as per your boundary conditions. And let us just see here. So F thermal, so for three-noded element, three-noded triangle, three-noded triangle. So what we have here, F thermal for the element is nothing but this is B transpose D, and this is epsilon thermal, which is nothing but alpha delta T. So continuing this one, so this B transpose is nothing but so this is the B transpose, okay, and D here is D11, 1, 2, So you can, this is our volume of the element. And since all these things are constant, so it is simply the dV will become volume of the element. And here these things, so this is nothing but d11 plus d12 alpha delta t. So this has to be multiplied with this one. So what happens here is that in fact, if we are using d22 as same as d11, isotropic material, so we can take that out and alpha delta t. So it is simply Bi, Ci, Pj, Cj. Okay, so this is how it is. I'm just did it, and area times thickness T. So this is what F thermal is. Once you have this, so you can assemble it and then solve here in the usual manner. And of course, evaluation of the stresses, actually finally if you want to evaluate the stresses within each element, then what is that which we need to take into account? So we have to take the stress, if you recall, it was this one. So stress was sigma is equal to d times epsilon mechanical, which is the total strain minus the thermal strain. So that means that's where the difference comes, and we'll illustrate it with respect to one example. So what we had found out here is the displacements of all the nodes. One thing I was telling is how to evaluate the stresses. So to evaluate stresses in an element, so what we found out is that the stresses is here sigma x, sigma y, tau xy. Is equal to d times here we say that this multiplies the total strain is the total strain minus thermal strain. So this is the equation for that, and so this is nothing but as usual epsilon V times the total displacements minus this is what alpha delta t So this is how we evaluate the stresses in the element. So that's nothing but the total total strains minus the thermal component here. So that will lead to the mechanical stress generated. Of course, this is a combined one. So, but this is how we arrived at So that is when we put these things in the potential energy formulation, this is how we did it, and then we had to bring back that equations to evaluate the stresses. So let us just do a small problem. Let's just do an example here. A simple example of just we take one triangular element. This is the same as our earlier problem. And I'm just taking it so that the calculations will be simpler. So what we have here, the temperature T naught is 25 degrees and heated to 125 Heinz modulus is 210 GPa. And alpha is I think this not right. Okay, so now what we have here is that we need to the rest of it is all same. So D here is 10 power 9. So now we have the same thing B as earlier. Okay, so that was B, and when we calculate F thermal, P transpose D and epsilon thermal. Okay, so using all these things, so substituting this B and D and epsilon thermal here is nothing but so alpha times delta T So calculating all these things, so putting the area of the triangle and all that. So we have okay. So F thermal of the element, you will get it as okay. So this is what you get, and we had K as earlier. This is the same problem as last time of the rectangular plate. K is the same as earlier. Okay, so this 6 by 6, and now what we can do here is that with boundary condition that the node 1 here is completely restrained and node 2 is restrained in vertical direction. So V2 is 0. So using this, we get U2 and U3 and V3. So then the stresses, as I was telling, so this is epsilon thermal. And this part is epsilon thermal, right? So using this, we get .9, 0.90, 10 to the power of minus 5. So I hope you have realized that the strain component here, this is the total strain, is nothing but your B times the nodal displacements of the element. Okay. So this all just follows that, and then this is alpha delta T, and then you evaluate this one to get the stresses. So that much you can do. Okay. So we'll stop at this moment and we'll continue with the new topic in the next class. So I hope you have followed how to evaluate the thermal stresses. So it is just the addition of your thermal load and then how to take care of that while calculating the stresses. So that is important part. Okay. I think I'll stop here and we'll continue in the next class.